Good day from ChemHelp ASAP. We are going to do a few examples of sp2 hybridized atoms. Okay, so on the screen we have a couple molecules and a grid, and let's finish off this grid. And since our molecules contain multiple second row elements, we'll have multiple columns per molecule. Okay, I think that'll work. Okay, so all these are going to be sp2 hybridized atoms. On the right, let's remember that when we think of sp2 hybridization, we have 4 atomic orbitals on each of these atoms, the carbons and the oxygens. And we want an sp2 hybridization. We do that because we need 3 hybrid orbitals. So we're going to combine the s and 2 of the p's, 3 atomic orbitals in, 3 new hybrids out, and then the p comes down, and we still have 4 atomic orbitals, 3 new hybrid orbitals and a leftover p orbital. So we need those 4 orbitals to satisfy the octet rule. Now, over here on our molecules, this first molecule, we have a carbon. That carbon has 3 attached atoms, 2 hydrogens and a nitrogen. So that'll be 3 attached atoms. It has 0 lone pairs. So A plus L equals 3. We need 3 hybrids. sp2 hybridization gives us that situation. And then the geometry of this carbon is sp2 is trigonal planar. And we would predict the bond angle to be 120 degrees. Now let's do the nitrogen, and then we'll see what the experimental angles are. For the nitrogen, we have 2 attached atoms. The nitrogen is attached to the carbon and the hydrogen, ignoring the double bond. We don't count the double bond twice. The number of lone pairs, it has 1 lone pair. Again, that gives A plus L equals 3. sp2 hybridization. This is as with 2 attached atoms in sp2, that is bent. And again, we predict 120 degrees. Let's label some of the bond angles in this structure. This bond angle, this is an experimental, but these are high-level theoretical calculations. So 118, 125, and can we squeeze that bond angle in there? This is 111. So all of these are pretty close to 120. So that's a pretty good match between our predicted bond angles and the experimental values. Now let's look at our molecule on the right. This is formaldehyde. Our carbon is attached to 3 atoms, 2 hydrogens and an oxygen. So that's 3, has 0 lone pairs. A plus L equals 3. We need sp2. Again, as before, this is going to be trigonal planar. Just abbreviating, and our predicted bond angle will be 120. The oxygen, now I said we don't normally assign hybridization of terminal atoms, but a lot of people do it, so let's just walk through it. That oxygen is attached to 1 atom, it's attached to the carbon, it has 2 lone pairs, so A plus L equals 3, and we would predict that this would be an sp2 hybridized atom. Now, since it's a terminal atom, it doesn't have a geometry, and it does not have a bond angle, and that's why you typically don't assign hybridizations of terminal atoms, because hybridization is about bond angles and geometries. But you still can go through the process of looking at bonds and lone pairs. So what are the bond angles in this molecule? Well, that bond angle from hydrogen to hydrogen is 118, and both of these bond angles, hydrogen, carbon to oxygen, are 121. So very close to our ideal value of 120 degrees. Hybridization, we can do this for sp3 hybridized atoms. We've seen we can do it for sp2, and we can also do it for sp as well. And it's a really accurate method for predicting geometries and bond angles.